Welcome to Tektronix Radar Testing Simplified webinar. Radar testing applications have special equipment requirements that often go well beyond general-purpose test equipment, including spectrum analyzers, oscilloscopes, and signal generators. Tektronix has application-specific softwares and solutions to enhance the performance of our general-purpose test equipment, making it ideal for many of the challenges of radar test applications. In this presentation, we will present a brief overview of radar operation and the challenges involved with the generation and analysis of radar pulses. This will include an overview of common tools used for testing radars. Important measurement parameters are discussed as they impact measurement results. And then we will focus the bulk of the presentation on the theory of operation for automatic pulse measurements that are available in the latest Tektronix oscilloscopes and spectrum analyzer products, including the innovative new impulse response measurements. Then we will briefly discuss the challenges and solutions for signal generation. In the most basic form, radars use a series of RF pulses that are turned on and off for a short period of time, then on and off again. As the signal travels to the transmit antenna, it then reflects off the target and returns to the radar. The reflected wave is then used by the radar receiver to discriminate the received signal information. Looking at the top example, the pulse width is too long to send back discernible targets to the receiver as the objects are close together. As shown in the second example, with a narrower pulse, to increase the target resolution, one can get multiple targets resolved in the return signal. With all other variables remaining constant, a narrower pulse width uses less power and can significantly impact the effective range of the radar. What's not shown is the pulse repetition interval, which needs to be considered to make sure that you're not taking into account and making sure that you're not talking when you should be listening. Thus, the operational modes of radar transmitters often have the most basic controls of pulse width and repetition frequency, or PRI, to allow for variable target tracking and range resolution. The time domain characteristics of the pulse naturally have their frequency domain equivalents. A narrow pulse width has a broader spectral shape than a wide pulse width. Similarly, a higher pulse repetition frequency will have larger spaces between the spectral line components than a slower PRF. Using a traditional spectrum analyzer for these measurements, you may already be familiar with this phenomena. For the example shown here, the frequency domain information can be translated back to the time domain of the pulse width 1 over the side lobe span, and the line spectra from the pulse repetition interval 1 over the PRI line spectra. To have correlated measurements of time and frequency, one must have an acquisition system with a sample rate and bandwidth and a memory depth able to collect the entire signal of interest. This includes the envelope rise time, correlated impulse spectrum, and the pulse train for a defined number of pulses. Historically, measuring radar pulses has often required multiple instruments: spectrum analyzers for frequency, vector analyzers for IQ vector signals, signal source analyzers for phase noise and microphonics measurements, oscilloscopes for timing, average and peak power meters for power measurements, and frequency counters. Tektronix spectrum analyzers and oscilloscopes use IQ vector acquisition for time sample data, enabling the correlated time and frequency information with the highest combination of bandwidth and dynamic range. In addition, our oscilloscopes have the highest instantaneous bandwidth and the greatest effective number of bits for doing measurements. Models are available to 20 gigahertz in bandwidth, enabling you to directly capture KU band radar signals without the need for additional down conversion or time-consuming calibration procedures. When combined with the signal view software, our oscilloscopes mirror the functionality analysis for high-performance spectrum analyzers, and the capabilities discussed in this webinar are available across all of our spectrum analyzers and real-time oscilloscope platforms, and they can replace the myriad of test equipment historically used to test radar signals. In addition to measuring radar pulses, we can also generate pulses to test receivers or transmitter components. The Tektronix AWG 5000 and 7000B arbitrary waveform generators provide industry-leading performance that can make pulses up to 9.6 gigahertz in bandwidth, sampled at 24 gigasamples a second. Single-channel, multi-channel, and digital interfaces are available for optimum flexibility in testing the different access points available in today's modern radars. Our RFXpress software with Option RDR radar offers the most advanced signal generation software available for radar transmitter emulation and receiver testing. Before talking about the radar test measurements themselves, I'm going to give a brief update of the real-time technologies that have been introduced in the last year. To better understand the unique capabilities of real-time spectrum analyzers, it's instructive to briefly examine the block diagrams of the three basic types of spectrum analyzers available today. In the first example, a swept-tuned spectrum analyzer uses a swept-tuned local oscillator and a sweep generator to measure a power over frequency. A narrowband envelope detector and a video bandwidth filter are used to be able to plot instantaneous power as you sweep across a signal of interest. The signal is passed through a resolution bandwidth filter, which limits the instantaneous bandwidth of the signal that can be viewed. A modern vector signal analyzer architecture is shown in the middle, and it converts the available spectrum using a stepped LO. The VSA then digitizes the wideband signal into the time domain and stores it into memory, converts it into the frequency domain, and displays the spectrum. In the bottom example of a real-time spectrum analyzer, many of the elements of the vector signal analyzer are similar. However, the real difference is the parallel path and the real-time processing engine that provides for real-time functionality and unique capabilities with regards to display, triggering, and analysis of signals. One of the technologies that utilizes the real-time processing engine is the DPX Transform Engine. DPX stands for digital phosphor. With the DPX Transform Engine, analog signals are converted down to a baseband, then go through an A to D, and are sampled at 100 to 300 megasamples a second. Discrete Fourier transforms are processed sequentially and overlapping on the incoming signals at a rate of up to 292,000 discrete Fourier transforms per second. The sequential FFTs are put into a pixel memory buffer and collected to be able to transfer to the display at a rate that keeps up with the incoming information. So at each time, between 10 and 33 times a second, you can transfer up to 14,000 images with a pixel memory count of the hits involved with the display. This gives you 100% probability of seeing any signal that is on for a duration of 10.3 microseconds. There's been some major enhancements in real-time technology and DPX technology since its first introduction. Three major enhancements are the Transformational Swept DPX capability, which now enables the ability to sweep a DPX across the entire frequency band of the spectrum analyzer. DPX density triggering, which allows for signal isolation based on the statistical properties of the signal, and unique time domain triggering, which is a runtime processing triggering that involves time qualified and runt-based triggering. With Swept DPX, we can now sweep DPX up to 20 gigahertz, up to the full span of 20 gigahertz in our real-time spectrum analyzers. At 292,000 spectrums per step, we now have a higher degree of certainty of seeing any signal of interest across the entire span of the spectrum analyzer. In the example shown on this slide here, we see a very, very wide bandwidth signal with greater than 1 gigahertz of bandwidth. Inside of that signal, you can now see some discrete tones just off-center and on the far left of the screen. This is ideal for seeing signals within signals that are occurring at different points in time, spurious or interference signals. The next breakthrough that we've done is added the ability to trigger on the density or the statistical properties of the signal. While DPX, in and of itself, provides visibility to signals that no other analyzer can see. Now with DPX density, we're able to trigger and isolate those signals of interest based on the statistical probability of occurrence. In this example we show on this page, we have a multi-hop signal with one signal that occurs co-channel interference at some points in time during the acquisition. Those signals can be individually identified and isolated for further analysis. Time domain triggering has always played an important role in the isolation of pulse signals, and many times people have used an oscilloscope and a spectrum analyzer in zero-span mode just because of some of the unique capabilities of triggering that can be found in an oscilloscope. With the unique time domain triggering, we now get rid of the need to have a separate oscilloscope to provide triggering for the signals of interest. Time-qualified signals, with hold-off times can be defined, eliminating the need for false triggers. Also, runt triggers based on amplitude and time-qualified can help isolate signals of interest or specific patterns or pulse widths that want to be monitored over a longer period of time. These enhancements in our second generation DPX can be summarized as follows. A 6x improvement in the processing rate of DPX, going now to 292 spectrum updates per second, orders of magnitude faster than any spectrum analyzer available on the market. With this, it comes an improved probability of intercept for short duration signals down to 10.3 microseconds, 100% certainty. 8 billion values of pixel memory are now available to give for a softer color grading and more detail contrast of infrequently occurring signals, as well as a higher resolution. Now we have the ability to sweep across 20 gigahertz span in a 10 kilohertz resolution bandwidth using DPX. And then faster time to insight, signal isolation, both with the DPX density triggers as well as time-qualified and run triggers, enable time-correlated measurements and markers to be used quicker. From a test and measurement standpoint, it is always easier to create a known signal than measure something unknown. So we'll spend a little bit more time on setting parameters and analysis of unknown signals. Since automatic pulse measurements for radars must cover a wide variety and types of pulses, it is important that some signal conditioning parameters for the expected signal of interest are set for the most accurate and meaningful measurement results. Tektronix has innovated complex pulse measurements with over 27 automated short-frame individual pulse or long-frame multi-pulse measurements. Automated measurements improve the reproducibility of complex pulses with measurements such as rise and fall time, overshoot, droop, ripple, and pulse-to-pulse phase measurements. As previously mentioned, since we're often replacing multiple instruments, including spectrum analyzers, vector analyzers, signal source analyzers, oscilloscopes, and parameters, and frequency counters, with a single tool, to get the same accuracy as those dedicated tools, it is often necessary to find some additional parameters representative of those instruments. These include things like a measurement filter, the bandwidth of the measurement, power thresholds, minimum off and on time, and the number of pulses. With segmented memory, we can handle up to 64,000 sequences and process up to 10,000 pulses at a time for measurements. When considering the setting of pulse measurement parameters, the user interface for the automatic pulse measurement tool provides the flexibility to analyze a variety of complex radar pulses. In addition to filter, bandwidth, threshold, and timing information, other parameters such as defining where the measurements are to be made or how they are to be calculated enhance the usability of automatic measurements in order to replace older tools. It is important to note that the measurement parameters will impact the displayed results, but do not actually impact the actual acquisition data. You may change the parameters and recalculate the results without needing to reacquire a new set of data. This includes the ability to save and recall at a later period of time, get reproducible results with different analysis parameters. Some advanced radar pulses use complex digital modulation techniques. It is possible to perform pulse-to-pulse analysis using signal quality, EVM, constellation, and symbol decode of complex signals with modulation analysis software available on our spectrum analyzers and signal view software. Over 30 common standard modulation formats are available with flexibility for proprietary modulation implementations. As with modulation analysis of common radio signals, to demodulate these complex signals requires the setting and associated modulation parameters of symbol rate for interpolating and resampling, measurement, filter, receiver or reference filter, and the alpha or beta filter coefficients. Once the measurement parameters are set, the next step is to discuss the theory of operation for the automatic detection algorithms. While this subject has been greatly simplified to the top 4 parameters for this presentation, more detailed explanation is included in our Fundamentals of Radar Measurement primer that we referenced at the end of this presentation. The simplest way to detect the existence of a pulse is to generate the histogram of the magnitude versus an acquisition record. If the pulses are relatively clean and have a good signal-to-noise ratio, there should be a bimodal distribution on the histogram. A large grouping will appear in the center on the noise level if present during the off time, and if the duty cycle is less than 50%, a lesser grouping will appear at the center or the top level of pulse. If the magnitude histogram method works in most cases, a pulse can be detected, and this is the fastest form of automatic pulse detection. However, there are potential problems with sole reliance on the magnitude histogram. Not all signals have good signal-to-noise ratio. Not all pulses have good signal-to-noise ratio. Some pulses are very, very narrow, and especially when looking at signals over the air, you could have variable levels of signals, which make it more difficult for an algorithm to see a bimodal distribution of the histogram. For this reason, the automatic pulse detection algorithm that we employ uses several methods to discern the existence of a pulse. The first method, the simplest method we've already discussed, was the magnitude histogram. Then we use a series of more complex and more time-consuming methods to determine if there is a pulse, using method 2, local statistics, a moving average. Then by process of elimination that there is a pulse, we use a noise histogram before going on to the last method, which is the least squares fit method. The local statistics involves the deployment of a sliding sampling window, and it's good for slow transition times, but does require high signal-to-noise ratio. Another method is a moving average, which is good for low signal-to-noise ratio, but does not work very good for very narrow pulses. Before you go on to the least squares fit, which is the most time-consuming method, the noise histogram looks for a non-Rayleigh distribution of noise to determine whether or not there's a signal present. The last method of detection is called the least squares method. It was devised to improve the ability to find pulses which are narrower and have a lower signal-to-noise ratio. For speed and increasing the probability of detection, if the user can enter the basic modulation type, whether or not it is a CW or linear frequency modulated chirp, then the algorithm can use this knowledge to greatly increase the probability of detecting the pulses that are in the noise. The example of the upper pulse shows a CW pulse with linear phase versus time. The example in the lower pulse with a parabolic distribution of phase is a linear FM chirp. The least squares method uses a sliding window, and the example shown here to fit a linear chirp against the incoming noise. You can see a parabolic distribution of the noise and also discern a frequency offset involved. The example on the bottom shows a low signal and noise ratio signal, and by doing the sliding window, you can now see a linear phase distribution, a straight line, instead of a parabolic curve. Once the pulses are detected, now we can model and construct the 4 cardinal points and the 4 lines necessary to create all the measurements. These cardinal points are the bottom of the rise time, the top of the rise time, the top of the fall time, and the bottom of the fall time. The lines are the slope of the rise time, the slope of the on time, the slope of the fall time, and the slope of the off time. A pulse cannot be determined to be a pulse unless a subsequent rise time is found on a second pulse. There are different methods employed for the estimation of frequency. There are 3 basic methods that can be considered. The first is a pulse with a constant phase. The second, commonly deployed in hopping signals, is a changing phase on each signal. Third is frequency estimation based on a linear chirp, whereby the low point of the parabolic distribution is interpolated over time. And the fourth is, if you know the frequency, you can enter it. There's been a recent enhancement that's been added to assess linear chirps, and this is the impulse response measurement, or the time side lobe measurement. You can think of each of the discontinuities that exist in a transmitter, from the generation of the signal, up converter, driver amplifier, power amplifier, and even at the antenna. If there is an imperfect match at any of those junctions, you get a reflected signal, an attenuated, reflected, and time-delayed signal. This is called an impulse response, a triple return, or time side lobe. We have automated the ability to see these time side lobes by convolving the signal of interest using a single port measurement. While currently we implement this solely for a linear chirp, the basic concept is that the time of the analysis is 1 over the bandwidth. The reason that this method works versus the other methods, frequency versus time cannot see overlap signals, and the spectrogram cannot compare 2 signals in FFTs of the same frame length, FFT frame length, and time resolution. Impulse response shows the time and amplitude together. In this example, we have a linear frequency modulated chirp that's been deconvolved to show the 100 megahertz wide chirp and a 1 microsecond delayed reflection that is down 30 dB. The same spectrogram of an FFT frame, 30 microseconds using a 1 megahertz resolution bandwidth, does not show any perturbation of the signal. The calculations for IPR go as follows, following the block diagram in the middle of the slide. After the RF pulse is digitized, a time window is applied to reduce the unwanted side lobes. The resultant FFT mathematics are input signal, and the finite time is not limited. For IPR, a Taylor window is used for good comparison between the lobe and residual side lobe levels. After the windowing, an FFT or other discrete Fourier transform is performed, give the frequency domain intermediate result. This spectrum is multiplied by the complex conjugate of an ideal chirp that de-chirps the pulse. The ideal chirp can be estimated by measurement routine that is the best fit against the incoming signal, or the user can either enter the details of an ideal chirp slope for more accurate measurements. After the manipulation and the multiplication, an inverse FFT is performed and transformed back into the time domain, and the result is the standard impulse response plot. The last block applies to the amplitude correction for the IPR plot. This plot here shows a time side lobe 40 dB down that is delayed by 1 microsecond. As the main pulse has a duration of 10 microseconds, this determines the total time span of the IPR measurement. It's important to note that internal mismatches are not the only phenomena that can be seen. Other distortions or incidental modulations, such as cross-coupling, can be represented. These may be difficult or impossible to see using common FFT analysis methods using spectrum analyzers, as the minimum time resolution of an FFT is the time occupied by the entire frame of the digitized samples used by the FFT. These things, such as incidental amplitude AM modulation and FM modulation, can often be unique identifiers of a specific radar and be used to classify that type of radar. Next, we look at this common applications and parameters for generating signals. It can be assumed that all of the parameters we have discussed in signal measurements also relate to signal generation capability. But with a flexible signal generation tool, ideal pulse signals can be created with signal generators that have the necessary performance to create the representative waveforms. In addition to creating ideal signals, it is often desired to create impaired or non-ideal waveforms to test component margins or to test receiver target recognition algorithms of scenes that might be encountered in the real world. To break this down into separate requirements, transmitter stimulus testing is often used to select components such as upconverters, amplifiers, and linearizers. One might also want to use a signal generator as a block substitution for the actual radar applications, such as radar cross-section analysis. Receiver validation is important not only for test sensitivity, but also the blocking and selectivity that might be anticipated from common interference sources. Receiver functionality can also be performed for scene generation, such as target recognition, the presence of common countermeasures. Test tools also need to be flexible, with the ability to test the access points, be it they digital, analog, baseband, IQ, IF, or directly at microwave frequencies. In addition to synthesis of known signals, the flexibility to import waveforms from common DSP tools such as MATLAB, or be able to replay captured data from acquisition tools such as spectrum analyzer or oscilloscopes may also be considered. While the Tektronix AWG can interface to the physical test plane, the RFXpress Option RDR software offers unprecedented flexibility in the creation of radar waveforms. Radar signals can be directly synthesized in the pulse train, or pulse groove formats for a variety of common modulation types and formats are also available. In addition to creating ideal signals, common impairments can be used to test component margin or receiver performance. If a desired waveform cannot be directly synthesized with Option RDR, it can be imported from common DSP tools widely used in the industry and replay captured data from oscilloscopes and spectrum analyzers. The user interface provides the tabular inputs for common pulse parameters with graphical descriptions of the definitions used in the terms. This is shown in the upper graphic. Within minutes, you can create complex Barker codes, polyphase codes, ideal chirps, and hopping frequency patterns that are directly synthesized by the AWG. In the lower left example, we're creating a Barker code, while the measured frequency versus time plots are shown on a spectrum analyzer. The lower right example shows a frequency versus time overview, spectrogram, and the DPX spectrum of a synthesized frequency hop signal. Another example of common test signal generation pattern is creation of staggered PRI pulses. When target velocities correspond to multiple integers of the PRF, they're referred to as blind speeds. The terminology is used for a multi-target indicator, an MTI filter response that equals 0 at these values. Blind speeds can pose serious problems on the performance of MTI radars and their ability to perform adequate target detection. Using PRF agility by changing the phase repetition interval between consecutive pulses can extend the blind speed to tolerable values. Tektronix innovative test equipment reduces the uncertainty during the design process and delivers the confidence in the integrity of increasingly complex radar signals and designs. Tektronix radar solutions include waveform generation software that can synthesize, import, or playback captured waveforms into an arbitrary waveform generator. Arbitrary waveform generators that can generate signals at digital analog interfaces, as well as baseband IQ, IF, RF, and even directly synthesized directly into X-band frequencies. Signal analysis available on all of our platforms, our leading oscilloscopes and spectrum analyzer platforms. And with a common user interface that's available with 27 automatic pulse analysis, this helps to simplify tests and improve test reproducibility. This table shows the summary of the currently available tools for signal analysis for both our spectrum analyzers and oscilloscope platforms. For dynamic ranges greater than 80 dBc and rise times down to 17 picoseconds, a minimum pulse width durations of 400 picoseconds, a tool can be selected to measure the most challenging pulses. Each platform, our oscilloscopes and spectrum analyzers, have the highest combination of bandwidth and dynamic range, and we use patented display and triggering functionality to help discover and isolate elusive events for your design. Automatic pulses improve the test confidence and reduce uncertainty, and analyzing pulse waveforms does require time-correlated multi-domain analysis. This table shows a summary of the currently available signal generation tools, from simple function generators to high-performance arbitrary waveform generators. With deep memory, advanced sequencing, and wide bandwidth, the advanced radar signal generation synthesis software, Tektronix has the solution for the most advanced radar test signal needs. Flexibility to create the signal at digital, analog baseband, IQ, IF, and RF, synthesize high dynamic range signals, or directly to 9.6 gigahertz in bandwidth, and the ability for simple software creation for complex radar waveforms. More detailed information can be found about Tektronix specific solutions in our Radar Fundamentals Primer, which can be found at www.tektronix.com/radar. Thank you.